13.6 Energy Considerations in Planetary and Satellite. The outline of this video is as follows. We will begin by applying the principle of energy conservation to gravitational systems, deriving expressions for the total mechanical energy of objects in both circular and elliptical orbits. Building on this, we will determine the minimum speed an object needs to completely break free from a planet's gravitational pull, a concept known as escape speed. Next, we will explore an extreme case of gravity by examining black holes, introducing the idea of the Schwarzschild radius and the event horizon. We will conclude by looking at the orbital motion of stars within galaxies, showing how unexpected observations of their speeds provide strong evidence for the existence of dark matter. Let us now apply the principle of energy conservation to an object in orbit, which is a key tool for understanding its motion. The total mechanical energy of the system is the sum of its kinetic energy from its motion and its gravitational potential energy from its position. For an isolated system where gravity is the only significant force at play, this total energy is conserved. This means that as an object travels along its orbit, its speed and distance might change, causing its kinetic and potential energies to change. However, they always change in a perfectly balanced way so that their sum, the total mechanical energy, remains exactly the same. For example, think of a satellite in an elliptical orbit around the Earth. As it moves closer to the Earth, its gravitational potential energy decreases. To keep the total energy constant, its kinetic energy must increase, causing the satellite to speed up. The reverse happens as it moves farther away. Therefore, the total mechanical energy is a constant of the motion for any object in a stable orbit. We can now combine kinetic energy with gravitational potential energy to define the total mechanical energy of a two-body system, which is a powerful conserved quantity for orbital motion. The total mechanical energy, labeled E, is simply the sum of the kinetic energy, 1/2 mv², and the gravitational potential energy, which is negative g m/r. For an isolated system with no non-conservative forces, this total energy is conserved. This means the energy at an initial point in an orbit must equal the energy at any final point. For example, as a comet moves closer to the Sun, its potential energy becomes more negative, so its kinetic energy must increase to keep the total sum constant. Crucially, for a system to be gravitationally bound, like a planet in orbit, the total energy E must be a negative value. If the total energy were zero or positive, the object would have enough energy to escape to infinity. The essential result is that for any stable gravitational orbit, both total energy and total angular momentum are conserved. Let us now specialize our energy discussion to the important case of a circular orbit. For this specific type of motion, we can find a simple and powerful relationship between the kinetic, potential, and total energy of the systems. The key physical insight is that the gravitational force provides the exact centripetal force needed to maintain the circular path. Setting the gravitational force, G m/r², equal to the required centripetal term, mv²/r, allows us to solve for the kinetic energy. We find that the kinetic energy, 1/2 mv², is equal to the quantity g m/2r. Next, we substitute this expression for kinetic energy back into our general equation for total energy. The total energy is the sum of this kinetic energy and the potential energy, which is negative g m/r. The result is that the total energy for a circular orbit is negative g m/2r. This is a crucial finding. The total energy is negative, which confirms the system is bound. Also, the total energy is exactly 1/2 of the potential energy, and its magnitude is equal to the object's kinetic energy. Now let us generalize our energy discussion to elliptical orbits, which are the most common type of orbit in the universe. Just as with circular orbits, the total mechanical energy for an object in a-bound elliptical orbit is negative. The formula is very similar. the total energy E equals the negative quantity G, m, all divided by 2a. Here, the letter A represents the semi-major axis of the ellipse, which you can think of as the average of the closest and farthest orbital distances. This leads to a powerful insight. An orbit's total energy depends only on its semi-major axis, not on its eccentricity or how stretched out it is. While the total energy remains constant, the kinetic and potential energies trade off. At perihelion, the closest point, potential energy is lowest, so kinetic energy and speed are highest. At aphelion, the farthest point, potential energy is highest, so kinetic energy is lowest. The key takeaway is that the total energy of any bound orbit is constant and is determined solely by its semi-major axis. We can now apply the total energy formula to a very practical problem: calculating the work a rocket engine must do to move a satellite between two different circular orbits. The energy that the engine must provide is equal to the change in the system's total mechanical energy, which we call delta E. This is found by taking the final total energy, E sub F, and subtracting the initial total energy, E sub I. We can substitute our expression for the energy of a circular orbit, which is negative G, m, over 2 Rs, for both the initial and final states. After simplifying the algebra, the change in energy, delta E, equals the quantity G times m, all over 2, multiplied by the difference of 1 over R sub I minus 1 over R sub F. In the common scenario of moving a satellite to a higher orbit, the final radius, R sub F, is greater than the initial radius, R sub I. This makes the entire expression for delta E positive. Therefore, to move a satellite to a higher orbit, the engine must do positive work to add energy to the system. Let us apply energy conservation to find the initial speed an object needs to reach a certain maximum height. This calculation is a key step in understanding how to leave a planet's gravity entirely. Imagine we launch a probe straight up from the Earth's surface. We will treat the probe and Earth as an isolated system, meaning their total mechanical energy is conserved. The initial state is at the surface, where the radius is R sub E and the speed is V sub I. The final state is at the peak of the trajectory, where the probe momentarily stops, so its speed is 0 and its radius is R max. The first equation on the slide simply states that the initial total energy equals the final total energy. On the left, we have the initial kinetic energy plus the initial potential energy. On the right, we have only the final potential energy, because the final kinetic energy is 0. When we solve this for the initial speed squared, we arrive at equation 13.21. Notice that the mass of the launched object, little m, cancels out during the derivation. This powerful result connects the required launch speed directly to the desired maximum altitude, independent of the object's own mass. Let us now formalize the concept of escape speed, which is the minimum initial speed an object needs to completely break free from a planet's gravitational pull. To derive the formula, we consider the case where an object travels to an infinitely large separation distance, at which point its final speed approaches 0. This specific trajectory corresponds to a total system energy of exactly 0. By setting the sum of the initial kinetic and potential energies to 0 and solving for the initial speed, we get the escape speed. For an object at the surface of the Earth, the escape speed, VESC, is the square root of the quantity 2 times g times the mass of the Earth, all divided by the radius of the Earth. Plugging in the known values, this speed is approximately 11.2 kilometers per second, or about 25,000 miles per hour. A very important and perhaps counterintuitive result is that the escape speed does not depend on the mass of the object being launched. A tiny satellite and a massive spacecraft both need to reach this same speed to escape Earth's gravity, assuming we ignore air resistance. The escape speed is determined only by the mass and radius of the planet you are leaving from. The formula for escape speed can be generalized beyond Earth, and this helps us understand a fascinating question. Why do planets have such different atmospheres? The escape speed from any planet with mass, m, and radius r, is given by v sub esc equals the square root of the quantity 2 times g times m, all divided by r. Now let us connect this to the gases in an atmosphere. The molecules of a gas are in constant random motion. From the study of heat, we know that at a given temperature, lighter molecules like hydrogen and helium have a much higher average speed than heavier molecules like oxygen and nitrogen. If the average speed of a gas's molecules is a significant fraction of the planet's escape speed, that gas will gradually leak away into space over time. This is why Earth held onto its heavier nitrogen and oxygen, but lost most of its early hydrogen and helium. In contrast, a gas giant like Jupiter has a very high escape speed, allowing it to retain even these lightest and fastest moving gases. Therefore, a planet's escape speed acts as a gravitational filter, determining which gases it can hold onto to form its long-term atmosphere. When a very massive star collapses, its gravity can become so overwhelmingly strong that nothing, not even light, can escape. If a star's core has a mass greater than about 2 to 3 times that of our Sun, the neutron degeneracy pressure that forms a neutron star is not enough to stop the collapse. The core continues to crush down into an incredibly small volume, creating an immense gravitational field. This leads us to a critical boundary defined by the Schwarzschild radius. This is the specific radius from the center of the mass where the escape speed becomes equal to the speed of light, c. The formula for this radius, rs, is 2 times the gravitational constant g times the mass, m, all divided by the speed of light squared. The imaginary sphere at this radius is called the event horizon. It is not a solid surface, but rather the ultimate point of no return. Anything that crosses the event horizon is trapped forever by the black hole's gravity. This slide highlights a profound mystery that arises when we compare orbital mechanics in our solar system to the rotation of entire galaxies. In our solar system, nearly all the mass is concentrated in the Sun. As a result, the law of gravity correctly predicts that a planet's orbital speed decreases as its distance from the Sun increases. This is why inner planets like Mercury orbit very quickly, while distant planets like Neptune move much more slowly. We would naturally expect this same principle to apply to galaxies, where most of the visible, luminous matter is concentrated in the bright central core. However, observations show something completely different. For stars and gas clouds far from the galactic center, their orbital speed remains nearly constant instead of decreasing. These objects are moving far too fast to be held in orbit by the gravity of the visible matter alone. This enormous discrepancy between prediction and observation is known as the galactic rotation problem. The flat rotation curves we observed for galaxies present a profound puzzle, leading physicists to propose a radical new idea: the existence of dark matter. The fact that stars in the outer regions of a galaxy are moving so quickly implies that there is far more gravitational pull, and therefore more mass, than can be accounted for by all the visible matter like stars, gas, and dust combined. To explain this, the hypothesis suggests that galaxies are embedded within a massive, spherical halo of this unseen substance. This dark matter halo extends far beyond the visible galactic disk. This substance is called dark because it does not appear to interact with light or any other form of electromagnetic radiation. We can only infer its presence from the gravitational force it exerts on the luminous matter we can observe. Similar evidence is also found when studying the motions of entire galaxies within galaxy clusters. While the nature of dark matter is one of the biggest unsolved problems in physics, Its existence is the leading explanation for the structure and motion of galaxies. Let us summarize the key energy concepts for objects in a gravitational field. The total mechanical energy of a two-body system is the sum of its kinetic and potential energy, given by E equals 1/2 mv squared minus the quantity g mm over r. For an isolated system, this total energy is conserved. For bound orbits like planets around the Sun, the total energy is always negative. In the special case of a circular orbit of radius r, the energy is E equals negative g mm over the quantity 2r. For a more general elliptical orbit, the energy is given by E equals negative g mm over the quantity 2a, where a is the semi-major axis. To escape a gravitational field completely, an object must have a total energy of at least 0. The minimum initial speed needed to achieve this is called the escape speed. From a planet's surface, this is given by v sub esc equals the square root of the quantity 2gm over r. Finally, we saw how these principles apply on a cosmic scales. The unexpectedly high orbital speeds of stars and galaxies, known as flat rotation curves, provide compelling evidence for dark matter, a mysterious form of mass that does not emit light. Let us wrap up by applying our knowledge of orbital mechanics to these two conceptual questions. First, a satellite in a circular orbit gets a forward thrust, L. This adds energy, pushing it into a larger, elliptical orbit. If it later settles into a new, higher circular orbit, its speed will be lower. This might seem counterintuitive, but to be in a stable higher orbit, more of the system's total energy must be in the form of potential energy. This requires a lower kinetic energy and thus a lower speed. A satellite in a higher orbit moves more slowly. Now, what if the Sun collapsed into a black hole of the same mass? The key here is Newton's law of universal gravitation. The gravitational force depends only on the masses of the two objects and the distance between them. Since the Sun's mass and the Earth's distance from it would not change, the force on the Earth would be completely unchanged. As a result, the Earth would continue in its orbit exactly as before, demonstrating that gravity depends on mass, not on the density or size of the object.